So my plan for today's discussion is first I will go through the Fourier transformations and then I will go through the midterm 2 problems. Okay. Feel free to stop me if you have any questions. All right. So for the Fourier series, definitely this is important in physics and we almost use it every day. And I will provide two different ways to look at this kind of Fourier series, Fourier transformations. So first one, we can regard this kind of a Fourier transformation as a limit of the Fourier series, right? Basically, we know if we have a periodical function. So in this case, the period is L. Then we can expand this function using the series, sine, cosine, whatever. So this is what we did in previous class. What's this? Okay, so let's expand. We can also expand in this kind of exponential. It's easy to write down, so I just use this 2L over L, so 2 pi over L x and the Cn. Right? Here is 2 pi over L because the period is L instead of 2L. What else? Yeah, Cn is given by what? Minus 2L from minus L to L. Oops. I think it's this. Fx expansion minus I n 2 pi over Lx dx. Right. So this is for the Fourier series. How about the Fourier transformation? Fourier transformation is for non-periodical function. Non-periodical meaning that it's equivalent to say the period is infinite, right? Meaning, so imagine if you have a function has infinite period, meaning that you can draw anything you want within like this from minus infinity to plus infinity. So you don't have to. So there's no it's not a periodical function anymore. And in this limit, this Fourier series, what we wrote down here, will translate into the Fourier transformation. To say that, it's also quite straightforward. Let's say, so for fx infinity, you will say when L goes to infinity, we can write this guy as the fx equal to minus plus and what's the thing? It's g alpha exponential I alpha x dx, and for Cn, which is what's the way to do that? Minus L to L fx exponential minus I n to x at when L goes to infinity, meaning that the function is non-periodical, then this guy becomes this this and fx exponential minus x dx. Oops, here should be df. Right. So, I mean, to say that we just need to, so let's look at this one first. The first limit. Let's just take a limit. So let's call this guy alpha. Then d alpha becomes 2 pi l, right? D alpha is the steps, like the increment, which is one. For example, n becomes n plus 1. Then the delta alpha is, n plus 1 2 pi l minus n 2 pi l, which is 2 pi l, 2 pi over l. Right? So, yeah. So when l goes to infinity, this delta l become infinitesimal small, and then this delta l becomes, this is what we learned in calculus. When this delta l becomes infinitesimal small, we just say it's dl, d alpha, d alpha, right? So we want, because so to make this guy become integral, we want d alpha here, but to make this guy invariant, we also want to divide by d alpha, right? D alpha is 1, so it's a equality, and Cn and exponential I alpha x. By the way, feel free to stop me if you get confused, and I can explain more. Otherwise, I just assume you understand what I wrote down here. And the alpha is 2L over, 2 pi over L, like what we, and this is,
Sorry, G, can I just ask again why you divided by d alpha?
oh, right. So basically, here I just rename our quantity. Originally it's n2 pi over L, and I call it alpha. And I want to construct an integration of alpha, so I want d alpha. On the one hand, I add this d alpha. On the other hand, I want remain this equation unchanged, right? Meaning that I want to divide by d alpha to make this guy unchanged. If I didn't divide by d alpha, then it's different because you times this d alpha.
Okay, that makes sense. Yeah.
So basically, I want, this is a very common trick. Like you times something, you divide by something, and then this guy becomes the a part of your integration, and this guy on the we know that d alpha is 2 pi over L, so we just write 2 pi over L, and combined with Cn is Cn L. And now, basically, the original variable is n. N is from minus infinity to plus infinity. Now it's like a change of variable. Now it becomes from n, becomes L. So L, remember L equal to m times 2 pi over L. So, sorry, alpha. Alpha is also goes from minus infinity to plus infinity, but it's a continuous variable. The difference is alpha is a continuous variable because you divide by L. L is infinite large. So now the variable becomes alpha. Alpha is from minus infinity to plus infinity. And let's call this guy, anyway, this is a function of n. And now, because we are doing a kind of a change of variable, we change n to alpha. So this is a function of alpha. So let's call this function as g alpha.
Could you repeat the logic on getting to the integral? I didn't quite catch that.
Okay, sure, yeah. That's quite important. Okay, so by the way, the trick we did here is very, very common when you go to, when you learn some more advanced class, like going from discrete version to the continuous version. That's the trick we did. Basically, so here, what we did is a change of variable. So originally the variable is n, and now we change a variable set alpha equal to n times 2 pi over L. So let's look at the range. Originally, the n is from minus infinity to plus infinity. Now it's also minus infinity to plus infinity. This is the reason why the integration range is from minus infinity to plus infinity. And then let's look at the, let's look at what. So n originally is kind of discrete value, right? It's minus 1, 0, 1, stuff like that. That is the reason why originally we have this kind of a sum instead of an integral. But let's look at alpha. Alpha is a continuous variable. Why is continuous variable? We only need to look at the increment, which is 2 pi L. By the way, the reason why n is discrete variable is because you can say the increment is 1, which is kind of a constant, a finite constant value. But for this alpha, the increment is 2 pi over L, which goes to 0, meaning that it's a kind of a continuous variable. Continuous variable, a sum of a continuous variable becomes an integral. So this is the reason why we change this, this kind of a sum of n becomes an integral when we change your variable to alpha.
So do we need it to be non-periodic to assert this?
Of course, for a periodic function, you can also do this.
You can, but then how are we taking it to a continuous space? Because we don't have that same relationship with L.
Oh, so you mean for continuous, sorry, for periodical function? Okay, so for periodical function, it's more tricky. Generally, if you, okay, so yeah, the answer is when you do a Fourier transformation for a periodic function, you would generally get some dead functions. You know, the dead function is kind of special. Yeah. Yeah. Anyway, let's do this kind of non-periodical first, and then we will go back to periodical again, like to illustrate what I said here.
Sure, thank you.
Yeah, first you need to understand what I'm saying here. Basically, I'm taking the non-periodical limit, and that L goes to infinity. A very good question. What if it's periodical? Yeah. Anyway, so this is a logic behind this kind of Fourier transformation. It's just a change of variable, and just and because L goes to infinity, non-periodical, so it becomes a continuous variable, and we have this kind of integral form. So then this guy is exactly what we have here. And let's reproduce the second equation. So the second equation, we want to get this G alpha, right? What is G alpha? G alpha, and like what I defined here. G alpha is defined as LCN divided by 2 pi. And what's this? We know that Cn is this formula. Okay, so I just copy this formula here. Minus to L and Fx expression minus I2 pi n over L x dx, right? And you can say this L cancel out, becomes 1 over 2 pi L minus L 0. And remember, this is what we call alpha. And when L goes to infinity, this guy becomes minus infinity, this guy becomes plus infinity. So this is nothing but what we wrote down here. So is it clear what I'm doing here? Any question about this part, this derivation?
I'm sorry, I'm just not sure about in what cases we need to do the change of variables that you just went over.
Oh yeah, so here here I just want to illustrate how we get the Fourier transformation from the Fourier series. And to achieve that, we need to do this kind of change of variables. And yeah, this is just a one way to view this kind of Fourier transformation. You should definitely regard this kind of Fourier transformation as a kind of a independent technique. And yeah.
Okay, thank you.
Yeah, definitely this is just one way to get this kind of Fourier transformation. So back to the question, what if the your fx is periodical, right? So in that case, let's say let's assume fx a very simple periodical function, which is x, sine x, right? Then what's this? Then what's this kind of a transformation you get? Sine x, right? fx becomes sine x and exponential minus fx dx. And what's this? What's this? This is quite easy. By the way, you should know how to do this kind of integral, which is you write in terms of ix minus ix. You may think this kind of a calculation is trivial, but it turns out it's very, very common in your futures class. 2i, and so this is exponential I 1 minus alpha x plus minus exponential I minus I 1 plus alpha x dx, and which is 2i. Stop me if you get confused. I just keep writing some equations. So what's this? This is nothing but 2 pi delta alpha minus 1. What's this? This is also nothing but 2 pi delta 1 plus alpha. So this is proportional 1 alpha minus 1 minus delta alpha plus 1. So you can say whenever you have a periodical function, and after the Fourier transformation, it will always pick up your your frequency, which is 1 and minus 1. So basically, so in your original space, which is x, fx in this case is sine x, and looks like this, right? And in your frequency space, sorry, in this kind of alpha space, let's call it alpha.
Sorry, can you go up a bit? Like I still, yeah. How did you transform the delta?
You mean from this step to this step?
Yeah. There is a transform of negative sign, right? Like
there's
in the.
Oh, you mean here? Or where? You mean?
Yeah. Why is the delta alpha minus 1? I get confused here.
Wait, you mean here from where? This one or this one? The first one or the second one?
I don't know both. Sorry.
Okay, sure. Let's maybe okay. So you know first, do you guys know what is that function? So that function is invented by Dirac. Sometimes it's also called Dirac that function, right? He invented this kind of that function to describe the density of a point charge. Basically, if you have a point charge and you want to calculate the density of this kind of point charge, let's call the point charge has charge 1, and at one point. According to the definition, we know that it's given by that Q divided by that volume. If X not equal to this point, let's call point A, then it's 0 because there's no charge. However, if your X equal to A, the point charge, total charge at this point is 1, but the volume is infinitesimal small, so it's infinity. So basically, in this case, your rho X becomes, assume this is A, this is the X axis, it becomes infinity at A and 0 at other places. And but if you integrate this guy over the space, you would get 1 because the total charge is 1. So that's it. So basically, that function is a function which is infinite at some place, but the area under this guy is 1. So that's it. That's the that's how we define that function. And it's, by the way, it's also an even function. Sorry, even, I mean, if we place that function at this place, it's even. You can say it's kind of an even function. Okay, so let's back to what we talk about, what we did here. There's one equation which is very, very useful. Okay, so kind of cloudy, so let's put it here. Minus infinity plus infinity minus I kx dx. This is given by 2 pi delta k. This is a very useful formula. You should always remember. So if we have this equation, then we know that this guy becomes delta 1 minus alpha. And what I said before, this is an even function. Oops. We can put a minus sign in front. It doesn't matter. So that 1 minus alpha becomes delta alpha minus 1. It really doesn't matter. And the same thing here. It should be delta minus 1 plus alpha. And I can put a plus minus sign in front, so it becomes delta 1 plus alpha. So
oh, I see. Thank you.
Yeah, any other question about this part, like about this kind of dead function stuff?
There's a trig form, obviously, which comes out of this as well. I don't see it immediately all the time. What does that look like? Because sometimes you get sine of n minus m, something like that.
Sorry, sine. What do you mean by that?
You can get the delta function as well from an integral over sine of n minus m, things of that nature.
Right. I mean, there are many different ways to express that functions. If you Google that function, I'm pretty sure there are many different ways, and you may get. You're right. There are some tricks. You mean like some sign, some stuff like with the integral, you get that function.
Mm-hmm.
Yeah. I think, okay, from my experience, I think the most useful equation is this one. And if you have this kind of a sign stuff, you can always write your sign as exponential minus exponential. I think you may reduce this expression to this.
Great, that's what I thought. It's been coming up and I'm just not seeing it immediately all the time. And so I was just curious if there was an
I said,
Thank
I'm pretty sure this is the most useful one, and you will meet this equation when you learn quantum mechanics. I'm pretty sure. And yeah, so okay, so let's back to this kind of a periodical function, Fourier transformation. For a periodic function in the x space is periodical like this, sine x, right? In the after the Fourier transformation, it's kind of another space. We call it alpha. This is what we call, and it becomes a two dead function. One is at 1, another one is at minus 1. Like this. What this mean? This just tells you your original function has only frequency 1. And of course, -1 is, you can, it's just because your original function is what? Your original function is a odd function, so there must be a counterpart in this -1 place, and that's it. If you have a function of sine 2x plus like a sine 4x, if you have something like this, without doing any calculation, you know that after you do a Fourier transformation, you would get some that function at 1, some at that function at 2, and at that function at 4, and of course corresponding minus frequency like this. That's it. So this kind of Fourier transformation just pick out.
Is that frequency?
Yeah. I mean, if you replace this x with t with time, then this 1, 2, 4 just a frequency, and this omega is this alpha is a frequency. If you use x, like regard x as the space, the space coordinate, then this alpha is what we call the momentum, or the k. What's the name? The k is the what's the name? What's the vector? The wave vector, something like that. I didn't remember the name, but anyway, yeah, it's k is proportional to the momentum p. There's a h bar difference, but anyway. So you can say basically the frequency, the Fourier transformation just pick up your period. Sorry, your frequency. Basically is 2 pi over your period. So there's a part which is kind of with a frequency 1, and there's a part with frequency 2, and there's a part with frequency 4. Then it's just some dead function there. If it's a non-periodical function, then generally it's not a dead function. It's something, yeah, normal. That's it. Any question about this part?
Sorry, what is delta Q over delta V again?
Delta Q.
When you talk about the P here.
Okay. So delta Q over delta V. Delta Q is basically when you calculate the density, you choose a very small, like a infinitesimal volume, and look at the charge within this volume and divide by this volume. You get this kind of density at this point, right? This is how we define density. And for point charge at A, when you look at the position outside this point, then there's no charge inside this volume. So this guy is 0, you get 0. But if you look at this point A, the total charge inside this box is 1 because it's a point charge. And that Q is that, that V is that V, is the volume. And you take the limit, and this delta V goes to 0, and then this density becomes infinite. And yeah, that's it. Is it clear or still unclear?
Yes, thank you. So does delta Q, sorry, equal to a specific value here?
So delta Q here is 1. Sorry, for point outside the this kind of point charge is 0. Right at this point charge is 1.
Okay, does it have an equation associated with it in this Fourier transform, or just this is just like a conceptual?
Kind of a separate stuff. So here, what I want to illustrate is that function. How we get this delta function? So that function is originally invented by Dirac to describe the density of a point charge. So what I'm trying to do here is like, if I have a point charge, what's the density? Like this. And it's independent of what we are doing here. Like,
I see, thank you.
So any other questions? Okay, so another way to view this kind of Fourier transformation, which I find is more useful, is like, okay, so let's write down this kind of Fourier. So switch alpha x, J alpha, J alpha, and by the way, let me write it down first. Different people have different conventions. Sometimes use this kind of this kind of convention. Sometimes people use this convention. Is in general, you can times a constant here and divide by constant here. It will not change the result. It will change your expression of your G alpha, but it really doesn't matter. Right. Let's use our the convention in the textbook like this. And then, so what I want to say here is this kind of a transformation, like you may think there's two functions, G fx and G alpha. They may, okay, it's actually very similar to what we did in the vector. So imagine we have a vector V, and we have some coordinates. Let's call this coordinate as some coordinate. Now the same way, of course, we can rotate your coordinate or translate your coordinate. Basically, I'm going to another coordinate, and we get if you express your V, this vector V, in this basis 1, you would get V1 and V2. And if you express the same vector V in this basis 2, you would get some different V1 and different V2, right? And let's call this V tilde. This V tilde is related with original V by some rotation matrix. And this is exactly what we did here. Imagine F is some abstract vector. F is some abstract vector. And originally we are in X space. Then imagine X is a continuous version of your 1, 2, 3. Basically, or so it's Vn. Then it becomes Fx, which is Fx. Of course, you can kind of write your F vector in different coordinates, which is alpha, and becomes F alpha, which is F alpha. Sometimes people also, here we denote as G alpha. So what I'm trying to say here is the Fx and the G alpha are the same thing that are viewed in different coordinates. So this kind of a Fourier transformation is nothing but a kind of a rotation, or in a more abstract way. So you can say this guy is Vi equal to, remember, this is a component form ij Vj, right? If you think of this kind of I as x, j as alpha, what's this? I as x, j as alpha, m, I is x, j is alpha, v, j is alpha. In this case, if alpha is a continuous variable, this becomes a d alpha. That's x alpha, v alpha. So you can say this guy, yes, copy. You can say this is, let's use another color. This is v tilde x, fx. This is the integral of alpha, This is m, is a function of x, and is also a function of alpha. This is nothing but this kind of exponential. This v alpha is nothing but this g alpha. So you can say this kind of a rotational transformation we have this kind of analogy with our Fourier transformation. And this guy, this inverse Fourier transformation is nothing but, from this guy, we know that V vector equal to this matrix inverse.
May I ask to explain it again? I'm kind of lost here.
Okay, so right. Let me see where should I start. So basically, what I'm trying to say here is, we know in the vector form we have a vector, and we can write a vector in different bases, right? Just stop me if you get confused. We can write a vector in different bases, and in different bases, the component is always related by some rotational matrix. Like this. Similarly, I have a function. You should think it as a more abstract, some function f. You can also express in x basis, and you can also express this in the alpha basis. Similarly, similar to what we have here, we have some d alpha. So you can imagine this d alpha, this integral of alpha is equivalent to this sum of j, and this kind of a function here you can think of as a kind of a rotational matrix, and this fx is the vector, is an analogy of a vector in some basis. This g alpha is the same vector in some different bases. Yeah, this is the analogy I want to point out.
All right, thank you.
Right. So the point is, there is an original function, there is a Fourier transformation, and this kind of a Fourier function. They're just the same thing viewed in different bases, and that means they contains the same information. And you know, there's a property like I didn't remember, like something like this equal to alpha, something like that, right? This is nothing but tells you if you use the vector analogy, this is nothing but tells you the magnitude of your vector is invariant in two bases. That's of course true. And also, because they contain the same information, if fx is an even function or odd function in your x basis, then your g alpha is also even or odd in this alpha basis. Yeah. So that's what I want to say about the Fourier transformation. There are two ways to kind of understand your Fourier transformation. One is regarding it as a limit of a Fourier series. And another one is view this kind of a transformation as a kind of a coordinate transformation, but in a continuous way. Yeah. So any question about this? Okay, so if you have no question, let's go to the midterm 2 problem. So I graded this problem 2, and another TA graded problem 1 and problem 3. Yeah, if you so let's skip the problem 1 first, and let's start with the problem 2. So problem 2 asks you to so what we know is the we have a function from 0 to L, and it's x. Now this part A asks you to expand this fx using the sine series with periodical 2L. That means you want to know what is the fx within this minus L to 0, because you want a sine series. So you want this guy to be an even odd function. So it should be looked like this. Should look like this, and then just standard stuff, right? Like fx equal to sum over n equal to 1 to infinity, bn sine pi over L and x, and the bn, which is L integration from minus 2L to L, but it's an odd function. So it's 2 times 0 to L, and your fx sine m pi L x dx, and you get some value. That's it. That's for part A. Any question? So right. So for the part B, very similar, because we want a cosine series. So we want this guy to be an even function. Basically, you have this, and the only difference. Okay, so you may take a look at the solution. It was posted on the CCLE. Oops. A naught r plus n of the 1 to infinity an cosine m pi over Lx. And you can calculate a naught, you can calculate an, use the standard equation, you know, the formula. Something here, I think this guy is L. Then you plug in, you get the final result. So for the part C, once you have part B, part C is quite straightforward. You just set your x to be 0, you get this guy. And right. So for the problem 3,
Wait, can I ask something about 2?
sure.
Why is it 2 over L instead of 1 over 2L?
Sorry, can you say it again?
For Bn, we have like the factor that it's 2 over L, right?
Yeah.
Shouldn't we have like 1 over the period, so 1 over 2L?
If it is the odd or even function, then you change the integral bound to 0 to L and you multiply by 2
Right. That's
if you make it even.
Yeah, but then the other 2 cancels out.
no. So
Integral minus infinity to infinity, yeah, to even function is 2 times 0 to infinity integral.
so first you need to know if you have a periodic function with a period, in this case is 2L, right? Then the Bn is given by L.
Oh, wait, someone answered it in the chat. Thank you. It's okay. It's clear now. Yeah.
Yeah, this should be L. As you can see. Cool. Right, this is for the problem 2. For problem 3, basically you want to prove this. What's this? You just draw the picture first. It's always helpful to draw this kind of picture. What's this? This is the when equal to pi, you get 0. Oops. When it's 2 pi, it's something like this. Yeah, something like this. This is pi over 2. This is also minus pi over 2. And you want to verify this is true. To verify that, you just do the Fourier series for this function, assuming it's a function with periodical 2 pi. So you can kind of draw this kind of picture, Then you know that this is an even function. Sorry, this is an odd function. So fx equal to n equal to 1 to infinity to Bn sine n times the omega x. Omega in this case is 2 pi over 2 pi, which is 1. So this is omega is 1, so it's nx.
I'm sorry, could you go over again how you knew what the function was that you're doing the Fourier series of?
You mean the problem 2?
No, for number 3. Like you just drew the graph. Like how did you know what the function was from 0 to pi? How did you know what it was?
Okay, sure. Yeah. You mean this can you mean this one?
Yeah, that one.
From 0 to 2 pi, this is given here, right?
Okay.
Yeah, this is your fx. Basically, you want to prove this function fx has a kind of a, what's like a expansion like this. That's what you want to prove. So we started with a function and doing the standard stuff, like doing this kind of a sine stuff, sine expansion. The reason why there's only sine part is because it's an odd function. If you assume the period is 2 pi, so you just repeat this kind of a graph, you see that it's an odd function. And the Bn, similarly, Bn is what? Is pi minus, this is minus pi, this is pi. So I just look at this part is minus pi to pi fx sine mx dx, and I can convert this kind of an integral to, because this is odd, this is also odd, so it's 2 0 to pi fx sine nx dx. And you know this, what is this fx? Fx is this guy. You plug here and you do the calculation and you get the result. And you finally find this this bn is 1 over n, I think. Right? Then you plug in, you reproduce this result. Then you verify that indeed it's true. And the second part asks you to like which value this series converge to at 2 pi. This is the what's the name of the theorem? It's Dirichlet theorem, I think. So basically, there it converges to the middle point of this kind of pi over 2 and minus pi over 2, which is 0, right? Which is 0. Right? And from this Euler series, prove this equation. Actually, you can do this part C without part A and part B. You just need to set your t to be pi over 2, I think. Right? Then immediately this Euler series becomes this series you need to prove. Yeah, that's it. Any question? Yeah, I think the time is up. So if you have no question, you are free to go. And if you have question, you can stay here. We can discuss.
Quick question.